In this video, we're going to take a look at the rational root theorem, which is something you might come across in a pre-calculus or math analysis type class. This, in conjunction with the long division / synthetic division that we did in another video on the channel, will help us find all of the rational roots of various polynomials, and we'll do that at the end of this video. First, before that, we're actually going to look at the rational root theorem itself. It tells us that if we have a polynomial function that we call f of x, defined as follows: q plus a1 up to the x to the 1, plus all the way up to p times x to the n, then it tells us that the possible rational roots of this polynomial function are plus minus the factors of q, which is this constant term, divided by plus minus the factors of p, which is the coefficient attached to this highest degree of x. Okay, so let's look at that in action really quick. Okay, so here we have our first example, and it asks us to find the possible rational roots of f of x equals x to the fourth plus 7x cubed plus 5x plus 10. Now notice, by the rational root theorem, what we want to do is factor the coefficients of the constant term and of our highest degree of x, which is here. But notice, this is an implied 1 out front of this x to the fourth term, and so the only thing we really need to factor is this constant term. So remember, the rational root theorem tells us that we need to do plus minus the factors of q divided by the factors of p, but in this case, those factors are 10 and 1. So here we're going to have plus minus 5, plus minus 2, plus minus 1, and plus minus 10 divided by plus minus 1. Okay, so that's going to give us plus minus 5, plus minus 2, plus minus 1, and plus minus 10. And these are your possible rational roots of this polynomial f of x. Okay, so now that we've done a really basic example, let's move on to something a bit more complicated. Okay, so here we have another example that asks us to find the possible rational roots of f of x equals 6x cubed plus 5x plus 12. So what we want to do is use the rational root theorem again, and so that'll give us an inclination that we want to factor this term, which is our constant term, and put it on top, and factor this term, which is our leading coefficient of our highest degree of x, and put it on the bottom. So factoring 12, we get plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6, and plus minus 12. So notice this 1 and 12 will go together to make 12, 2 and 6, and 3 and 4. Okay, but now we want to do the same for 6 on the bottom here. So that's going to be plus minus 1, plus minus 2, plus minus 3, and plus minus 6. But now, like before, we're going to take the top and divide them by the bottom. But in our last case, the bottom was just plus minus 1. Here what we want to do is take each of the top numbers and apply the bottoms individually. So what we're going to end up with is plus minus 1, plus minus 2, plus minus 3, plus minus 4, and so on. But then we're also going to have plus minus 1 divided by plus minus 2, plus minus 2 divided by plus minus 2, and so on and so forth until we've covered all the way up to plus minus 6. So let's go ahead and do that here. So that's going to be plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6, and plus minus 12. That's from this plus minus 1 on the bottom, so I'll go ahead and mark that out. Now we have plus minus 2, and that'll give us, let's see, that'll give us plus minus 1/2 from 1 divided by 2. It'll also give us 1 again from 2 divided by 2, but we have that here. We have 3 divided by 2, so that'll be plus minus 3/2. It gives us 4 divided by 2, but we have 2 here. 6 divided by 2, but we have 3 here. And 12 divided by 2, but we have 6 here. So we're good there. Now we need to divide by 3, so that'll be plus minus 1/3, plus minus 2/3, plus minus 3/3, but that's plus minus 1, plus minus 4/3, plus minus 6/3, but that's 2, and plus minus 12/3, but that is 4. Okay, so that's our 3 done. And now we have plus minus 6 left, so that'll give us plus minus 1/6, plus minus 2/6, but we have that already because that's equivalent to 1/3, plus minus 3/6, but that's equivalent to 1/2, which we have here, plus minus 4/6, but that's already on here as well in the form of 2/3, plus minus 6/6, which is 1, and plus minus 12/6, which is 2. So this list contains all of our rational roots, all the possibilities for our rational roots of this polynomial 6x cubed plus 5x plus 12. So what we'll want to do when we're finding the exact rational roots of polynomials like this is take these possible rational roots and test them using synthetic or long division, and then from there we should be able to simply factor when we get down to something like a quadratic. So let's go ahead and do an example of that. Okay, so this example asks us to find the exact rational roots of 3x cubed plus 9x squared plus x plus 3. So our rational root theorem is going to tell us that we need to split this up into the factors of 3 and 3. So that tells us we need to take a look at plus minus 3, plus minus 1, and also plus minus 1/3 that we get from this term divided by this term. Okay, so I think the simplest example is to look at x equals 1 or x equals minus 1. So we'll look at those two first. So we'll have x minus 1, and we'll test it using long division because that's my favorite method, but then we'll test x plus 1 here with synthetic division. So not 3x cubed plus 9x squared plus x plus 3, like that. And again, so we'll do some long division here. What do we need to multiply x to get 3x cubed? That'll be 3x squared. So 3x squared minus 3x squared. Subtract that, so that'll be 12x squared plus x. So this is going to be 12x here. So 12x squared minus 12x equals 13x plus 3. Moving this 3 down to here. And now this will be 13. So this will be 13x minus 13. This is going to be 0 plus 16. But notice this 16 cannot be multiplied by x, and so our remainder here is 16. But that tells us that x minus 1, or x equals 1, is not a factor or a root of this polynomial. So let's test x plus 1, or the root x equals -1 next. Okay, so I said I would test the next root with the synthetic division, so that's what I'll do here. So I have minus 1, and so I'll take minus 1 and multiply it by 3, because we always bring this first coefficient down. So that gives us minus 3 here, but that'll give us 6. And then we subtract 6 again here, so that gives us minus 5. But then -1 times -5 gives us 5 here, and that gives us 8. And again, we're looking for a 0 in this constant term here. So again, this root x plus 1 is not a root. Okay, so let's test something else. Okay, so here we're testing if x plus 3 factors nicely into this polynomial. So what we're going to do is multiply -3 by 3. That gives us minus 9, and that'll give us 0. But that gives us 0 from 0 times -3. So this 1 drops down like that. But then we get -3 times 1, and that will give us a -3 for a sum of 0. And we finally have a 0 in our constant term here, which means this factorization of this polynomial works, and it gives us no remainder. So this factors as x minus 3 times, and then these are the coefficients of our remaining quadratic. So we have 3x squared plus 0x plus 1. And so from here what we can do is use the quadratic formula on this. So our remaining roots are going to be x equals -b, which b in this case is 0, plus minus 0 squared minus 4 times a times c, which is 4 times 3 times 1. So that's going to be -12 divided by 2. And so because we have this -12 inside the square root here, that shows us that we're going to have some complex roots. I have a video on complex roots on the channel if you want to go take a look at those, but that tells us that our only rational root of this polynomial is this root. And I think that's enough for now.